Okay, are we all there?
Yep.
Yes.
Okay, good. Open the screen there. All right, well, this is for something completely different, and it's been very interesting to listen to the previous two talks, particularly when they are referring to the alteration styles at Mount Isa. Our area here is a area, hang on, I've got an issue. That's not working. I'm just going to get some help here.
Okay.
There we go. The background to this is the Collaborative Exploration Initiative Grant, the New Economy Minerals Initiative Round 3. This was a very hurried program, and we were granted some funds to do some drilling in a new style of lithium mineralisation in the Georgetown area. This is something we had just encountered, and what I want to do today is just take you through the history of discovery, because there are some interesting lessons, and I noticed particularly with Glenn, some of the comments that Glenn made really do resonate with what we're doing here. Just so firstly, some acknowledgements. Bradley Crichton, who's the Exploration Director, and Stephen Wilson, who managed a lot of this, have contributed a lot of this work. And to Dr. Rowena Duckworth of Mintech, who's did the Petrology for us. If you're out there, Rowena, I'll say hello and thank you for your work. So this is the area here. Forsyth is the town closest over here. Georgetown is just to the north here, and we go out the main access through to a station called Flat Creek. And this is a large mining lease that we've taken out here that covers the main area of the lithium interest. Just to give you a quick overview of the geology, we have to the east here a very, very large granitic intrusion, or it's called the Forsyth Supersuite. It goes quite a considerable way north, and it's broken down into various other groups. And over in this area here, which is the target area, we have late phase leucogranites that appear derived from this main supersuite. The other interesting thing to note right now is that we are in a metamorphic area which goes from upper greenschist facies, lower amphibolite. We're over here in about middle amphibolite through to upper amphibolite, and down more in these areas down here we get up to granulite facies. It is important, I think, that the country rocks at the time of our mineralisation were at middle amphibolite facies, because the style of mineralisation we've got, the transfer of heat is very, very important. And if you're trying to alter a lot of cold rocks, you don't get very far. But here we had compatible temperatures between the country rock and the late phase mineralisation. I won't go into a lot of detail on the geological setting, but this is the area over here that our main focus is. We call it the Buchanans Dome. One of the features in this area is this cobalt metadiorite, the purple. It is folded, it's literally geological origami, and there's three main periods of folding. Down in this area, the main schistosity runs in this direction, and the dome shape here is due to multiple folding. And we have some later carboniferous or rhyolitic flows, breccias, and we have a similar thing up over here. So that's the background to it. The history. Tin and tantalum were found in this area last century. Around about 1930, the tantalum was first identified. Back then you couldn't sell tantalum for love nor money, so they focused on tin, and also a lot of alluvial gold in the region. The region has been extensively worked for alluvial gold. Lithium was not even considered until 2011, when the first discoveries of some LCT pegmatites were made. And here's an example on the right here of a lepidolite outcrop. These are only small LCT pegmatites, quite massive lepidolite, grade very well, good tantalum contents, but they're not the subject of what we're exploring. The structural emplacement of this area is quite interesting. One thing I've taken away from the previous two talks is the importance of major structures. So here, I'll just run it up, we have this Glenrowan lineament running up through here and along here. We have another major lineament here, the tabletop lineament, running here and here. The main area for our lithium is in this sub-block here, which appears to have been raised and tilted such that the sediments are now dipping almost vertically. Over here we have the remnants or the main bulk of the Forsyth supersuite, divided here into the Forsyth granite. Here the ropework granite. Over here is a granodiorite, and I probably cheekily mention here that the GSQ has failed to map this one. Pegmatites all through the area, and here we have a suite of leucogranites, and these are the main source target. So that's something very important to note. Laurie Hutton, before he retired, did some work for us on the aging of these rocks in the district, and the Forsyth supersuite have been in place around 1550 million years. That was known previously, but a new age date for the leucogranites has come out around the 1442 event. So we've seen roughly 100 million years of period of differentiation of the major supersuite granites to produce these leucogranites. And here's an example of one of the leucogranites, very micaceous, very high in fluorine, and also tenfold anomalous in lithium in their background. So these are quite unique. Here's another sample of a pegmatite that was age dated, and it does appear that there are younger events throughout parts of the Georgetown area as well. So this is still very preliminary work. This was only done about 2018, and so we are still feeling our way. That was the first key finding. I'll just go back to that slide. I'll go through now the pathway to discovery. And the first step that alerted us to the potential of the lithium here was these younger lithium-enriched leucogranites. When we did some rough calculations, we came up with where is the lost lithium. We certainly couldn't explain the lithium that we saw in these granites with a few small LCT pegmatites. So that began our quest. We drilled some holes through the pegmatites, and I'll go across here to pegmatite drill hole number 2 first. We drilled, obviously aiming to get a lot of pegmatite, and these were the results. Metasediment, 0.35 lithium. Pegmatite, 400 ppm. Metasediment, 0.52. Pegmatite, 400, and so on. Why is the lithium in the metasediments? Naturally, we questioned ourselves. Oh, we've got the assays wrong. We've got the intervals wrong. We'll relog all of this and check it again. We then found, no, it's true. So we went to a hole that had been drilled in 2016 and not looked at, hole number 18. We thought this was a failure because we didn't hit very much pegmatite. And lo and behold, we began to hit considerable quantities of lithium right through the metasediments. And again, this is only part of the hole, but it'll give you the idea. Now, the first theory, and I hate theories before you get evidence, but the first theory was the pegmatites were shedding the lithium in a contact metamorphic sense. But anybody familiar with any thermodynamics will realize that 20 centimeters of pegmatite is not going to transfer enough heat to alter several meters of metasediment on either side. And this hole went on to be anomalous in lithium over 50 meters. And you can see here in the diagram here, this is the position of the holes, and we've got light areas here of schists that are turning out to be altered with lithium mineralization. So we began to look a bit further. We went back through our database and we pulled out numbers of examples of amphibolites, schists, and so on that were in the various drill holes we'd done when we were drilling the pegmatites for tantalum. And we started to get these sorts of figures. This is Li here. We also had very high fluorine and quite good barium. Cesium, which is very hard to move, quite high, and of course rubidium. We then went to the literature, thought we'd better know a little bit more about this, and we started to see, not so much in Australia, but overseas, deposits such as San Jose, Sadersdorf, Zinwald, and Synovec in the Czech Republic were quite large lithium deposits of a similar style where leucogranite had intruded the country rocks and the volatiles had streamed off, altering the country rocks and introducing lithium over bulk tonnage. So this began to get us on our way. How do we test this? Like elsewhere in a lot of northwest Queensland, there's soil cover and the rocks are often quite covered. So we trialled termite hill sampling. At first, people went out there and smashed a few termites' nests, tested them, and we found that we were getting lithium in the termite hills. So, being a typical pragmatist, I said, well, to hell with this. So we took a splayed drill bit and we just drilled these damn things and rapidly sampled this whole area. And over the top here, we have slates that are higher up in the stratigraphic sequence. And this is background, 50 to 70 ppm lithium is background. We got into here, into the yellow, and we have consistently high background. These are roughly 25 meter spacing. And this is the beautiful structure of the major S1 foliation folded around the top of the dome. It shows fault zones very, very neatly. These are LCT pegmatite there and there and there, which are the highs. Scale here about 500 meters across by roughly a meter in size. And this is elevation, and you can see the results down the bottom there. We then went back through our data of stream drainage sampling, and we began to find a pattern. This zone here is the one in the previous slide of the alteration up there with the lithium, and these are additional areas in the district. These have not yet been tested. I'm not quite so optimistic about ones up here, but the ones within this main block here are of particular interest. So we began to address the key exploration criteria that we needed: the presence of Luca granites, and of course associated pegmatites. If you've got pegmatites there, particularly if they have some LCT characteristics, that is a good sign. You need to do some careful field mapping and geochemical sample to try and establish the areas of the lithium anomalism. To confirm the presence of the metasomatic mineral assemblages in the country rocks, we needed to go to petrology. There's main alteration minerals are white micas. I'm not going to try and differentiate between lithium muscovites and the lepidolite group in here, but just call them white mica. You can do it if you've got X-ray vision, but I don't have. Biotite, chlorite, actinolite, and sundry carbonates. These mineral assemblages are clearly overprinting the peak metamorphic event around 1550 that was associated with the supersweet intrusives. The other thing that has come out of this is that the overprinting of the regional metamorphic and the relic igneous fabrics is almost complete. This is quite extreme metasomatism. But not all of the metasomatic minerals will actually scavenge the alkali metals efficiently. So what you're seeing is a very big dispersion of the lithium across wide areas. We've since, under this program, drilled a second hole, which has extended the area of metasomatism in that other slide by about 1 kilometre. So we then did some petrology, and this was from a sample in the hole 18, the discovery hole, if you like. And you can see here, this, I'll wriggle the cursor for you. This is the S1 foliation. This is the peak metamorphic event, and these are the micas and quartz. It's a quartz mica schist. You can very clearly see here overprinting of a later phase mica. This has a pinkish lemon pleochroism. We've microprobed these, and these contain the lithium here. So there's no lithium in the early part of the rock. The lithium is in this 100 million year later event, which has overprinted the major regional metamorphism. I'll go through some further slides with here to give you an idea. During our drilling, we went through sections of amphibolite. These are the cobalt metadolerite, and this is what really alerted us to the intensity of the metasomatism. These, outside of the area of metasomatism under the normal regional metamorphism, will show relic igneous textures. They'll show clinopyroxene, hornblende, plagioclase assemblage. We look on the left one here, and we can see recrystallized quartz. This is all actinolite here. There's been a lot of iron introduced. This is biotite. Over here, we have very coarse grain chlorite growth, carbonates shot through. These rocks are pretty well altered, and they're altered, so far we know, over thicknesses of something like 30 meters. So this is not a contact metamorphic effect. This is not something that's prograde regional metamorphism. This is very, very driven gaseous metasomatism. Here's another example. We've got here carbonates right through, very, very coarse chlorides. You can see this in the core as big star formations. This rock is totally altered. Here's another example. Under our model, we were looking at mica schist because we soon realized that it was the white micas that were scavenging the lithium, not the biotite, nor the chlorite, nor the actinolite, or the mixed carbonates. And by mixed carbonates, I mean they've got manganese, iron, magnesium in them. So they're quite a hodgepodge. So here we have on the left, plain polarized light, and the light, highly foliated material here is the mica, and the second generation overprint is biotite here. This is a disappointment, this one, because if it was the other way around, we have a very high grade lithium ore. But because this receptive mica here is first generation and predates the lithium metasomatism, we don't get it. And what we have here is dispersal in the biotite. That being said, these still run 10 times background. Over here, you can see it under cross polars. There's a lovely little garnet there to give you an idea of the metamorphic grade. Then we have the target rock. This rock here is a quartz mica schist. And for those of you who are got good eyesight, you'll see this is the regional foliation up along here. And you'll see the secondary generation of mica running here at about 30-degree angle. This secondary mica here only comprises about 10% of this sample, and yet it runs roughly 0.5% lithium oxide. This is our target rock. So the thing that's come out of our study so far is that the host rock composition is very, very critical when it's interacting with metasomatic fluids. So I'm not going to be talking as long as the others, but the new style lithium mineralization, as I say, this is only something that we've been working on since 2018. But the key points that we've already focused in on is the presence of lithium-enriched leucogranites. They are essential source. As these things are stoping upwards, and you've got large areas of country rock that are in tension, and so structure and structural pathways are being opened up as they stope forward, and we have intensive aerial metasomatism occurring, and importantly, we have fluorine and CO2 gases in there, and they are carrying with them the alkali metals. So we're getting lithium carried, we're getting cesium and rubidium. We are also getting potassium as well, and quite often in the aureole, the rocks will be tenfold potassium enriched. So in the metadolerite, for example, which will have a background of 0.3, 0.4% KTO, we can get 1 to 3% potassium in those rocks. So it is very much an alkali metal metasomatism. I mentioned the suitable structural features, also proximity to the source leucogranites. This is important, and the best way, of course, we can see that is with the presence of pegmatites, but not always LCT pegmatites bearing lepidolite. Many of the pegmatites are quite barren. They are in fact lower in lithium than the source leucogranites, and certainly lower in lithium than the surrounding rocks they're intruding. So we have a gaseous phase first, then the fluids, the volatiles, followed by the pegmatites. And once you have that system all working for you, the location of economic mineralization is going to be very dependent on the host rock composition. And we need to have overprinting of second generation mica, and this seems to very effectively scavenge and concentrate the lithium to ore grade. So in short, our conclusion, when we started out, we wanted to demonstrate real economic potential. Like most things, we have to step back half a pace, but certainly the geological potential does exist for the discovery of economic deposits of this style of lithium mineralization associated with the metasomatized country rock. So that's where we're at. We don't have a long history like Mount Isa. This is very, very new stuff, but with great hopes for the future that this style will be repeated through other parts of North Queensland. Thank you.